This week in Science 30, we are going to talk about nuclear fission and nuclear fusion and nuclear decays. This is a picture of a nuclear fueled power plant. This uranium fuel is unstable, it's radioactive, and so in order to become stable, it'll give off matter or energy, and in that process it'll get more stable. But as it gives off that matter or energy, they can use it to heat water and produce energy that way. Now there's three types of radiation that we need to be careful of. These are forms of ionizing radiation. So one, radiation is kind of a misnomer. Like any light that comes from the sun we can call radiation. However, the radiation that is harmful to people comes in three forms: alpha, beta, and gamma. This is radiation with enough energy to knock electrons or to create ions in the body, and those ions can then cause damage, tumors, or other kind of forms of damage. Now, their dangers and their penetrating abilities differ. Alpha has a very low penetrating ability. It's blocked by a piece of paper. It can only travel a couple centimeters in the air. However, it has a very high ionizing ability. So alpha particles are sometimes drawn like this. So they're helium nuclei. So they're just a helium. So a helium is 2 protons and 2 neutrons. That's our alpha particle, and then no electrons. So this is an alpha particle. So it's a relatively large form of ionizing radiation, which is why it has a very high ionizing ability. But because it's so large, it has a very low penetrating ability. The next is beta radiation, which is basically an electron. So this electron is a lot smaller than 2 protons and 2 neutrons. So it can penetrate more. It can get through a piece of paper, but it can't penetrate all the way through the body. That's beta radiation. So it's kind of in between when it comes to its penetrating and ionizing ability. It doesn't ionize as much either because it's only an electron as opposed to 2 protons, so it doesn't have as much charge. And it's also not as large, so it doesn't interact with matter as strongly. The last type is very highly penetrating, but very low ionizing ability, and that's gamma radiation. So gamma radiation is passing through your body all the time. It can really only be blocked by like very, very thick concrete. Gamma radiation will go through paper, your hand, water, and still continue on before it stops. It's a form of electromagnetic radiation. So it's on the electromagnetic spectrum. It's a very high energy, so very high frequency, very low wavelength when we talk about the electromagnetic spectrum. So a very high frequency wave. And because it has that energy, if it does hit something, it has the ability to knock ions off of that. Whatever atom it hits. So that's gamma. It's highly penetrating, low ionizing. So gamma is dangerous. It's dangerous because it has such a high penetrating ability. Alpha is dangerous because it has such a high ionizing ability. And beta is dangerous as well. It also is a form of ionizing radiation, and it's kind of right in between those two when it comes to both of those abilities. Now, alpha decay is one form of decay we need to recognize, and it is a decay so we have an unstable form of matter. So we can draw this notation like this, where this is the element, this is the number of protons, and then this is the total number, the mass number of protons plus neutrons. So we do identify different isotopes, which are things with different neutrons, by like saying uranium-235. So uranium-235 gives me that mass number. I know because it's uranium, it has to have 92 protons. That's what makes it uranium. So uranium-235 is unstable. One way that it reaches stability is through an alpha decay. So in order for this uranium-235 to become more stable, it'll actually shed an alpha particle, which is a helium nucleus. So you'll see an alpha particle like this. So this is an alpha particle. Or sometimes you'll see it with this Roman symbol alpha, 2+. So we'll give up an alpha particle. Now, one thing that happens in all of these decays that is really important is that charge, mass energy, so charge, mass, energy, and also the number, so the mass number has to be conserved. So when I look at this decay, so it gives up a helium nucleus. That means that if I had 235 neutrons and protons before, and I gave up 4 of those, that means that the new element that is produced needs to have 231 nucleotides, neutrons and protons. Charge has to be conserved as well. So before I had 92 protons, afterwards, so I gave up 2 protons to that alpha particle, which means that I need 90 protons in my, we call it a daughter, in my daughter element. So this would be thorium-231, which would be produced in this alpha decay. So an isotope of thorium. So when we do look at these decay equations, so this is an alpha decay, we have our decay particle, so there's our alpha particle. Our total number of protons and neutrons needs to be conserved, as well as our total number of protons needs to be conserved as well. So this is an example of an alpha decay, and in the form, some energy is given off as well. You do have some different isotopes on your periodic table. So if you look in your data booklet, so maybe this is uranium-235. On your chart, it's up here. So you can see kind of what it looks like. So an alpha particle. My chart, so I have 90 thorium. So this would be thorium-231. So if I have 90 protons. Cobalt has a mass, an atomic number of, it's not. So the next type of decay is a beta decay. Here we have cobalt-60. So this is cobalt with a mass number of 60, but it has 27 protons. And this, again, it's unstable. It reaches stability by decaying into nickel-60 with 28 protons. Now you'll notice that this is a little weird when we look at kind of what's conserved. When I look at the decay particle, so we're missing a decay particle here, 60 and 60, it has a mass number of 0. And when I look at what happens to the number of protons, I go from 27 to 28. So 27 to 28 means that my charge on this decay particle needs to be -1. So this is what we call a beta particle. We usually call it beta when we're talking about it in regards to nuclear decays. However, it's the same thing as an electron. An electron is a negative beta decay particle. So what's kind of happening here is I have a neutron. So one of these neutrons is actually breaking down into a proton and an electron. And there's another particle too, called an antineutrino. And this is needed because momentum, that electron is moving a lot slower than what they expect. And so then they created this antineutrino in order to conserve momentum. But we don't really need to know that. So we need to know that in a beta decay, we produce a beta negative decay is what we're going to be focusing on. An electron, we'll notice that our proton number goes up by 1, because again, I have 27 plus 27 here. It needs to be plus 27 on this side as well. We'll notice that the mass number of this decay particle is 0, because this needs to be conserved as well. And this is what happens in a beta negative decay. In our chart, you can see the beta particle is written as that, as an electron, or as that beta symbol. It both means the same thing. The last type is gamma decay. And now this is a form of electromagnetic radiation, so it's not a form of matter. So here we have barium-137. And in order to reach stability, it can give off a burst of energy. And that's our gamma. So this could be a form of gamma radiation. Now doesn't have any mass. It's a photon of light. So our mass number doesn't change, and neither does our proton number. It just has less energy afterwards. So this is gamma decay. So the first two decays, alpha and beta, are giving off matter. In gamma decay, it is just giving off a photon, or a gamma photon, in order to release energy. Now, when you look at nuclear energy, you're probably most familiar with like The Simpsons and those big cement columns that are giving off steam. The fusion the type of nuclear reactions that we do on Earth is nuclear fission. So nuclear fission is taking a neutron and we shoot it into uranium-235. This makes uranium-235 unstable. What it does then to reach stability is it breaks into two smaller atoms, and it also produces 3 neutrons. Now, these 3 neutrons are important because if we have a lot of uranium-235, these 3 neutrons can then go on and do this same reaction. So these 3 neutrons will undergo another fission with another uranium-235, which gives off another 3 neutrons. And then those 3 neutrons can go on to do more fissions. And we end up with this chain reaction where we produce more and more energy. That's how we release a ton of energy in like a nuclear bomb or some of these nuclear reactions. Now we can also control that. So in a nuclear reactor, we don't want it to run away like this and undergo a chain reaction. So they're careful about the amount of fuel that they're using, and they use water to control that, and how much actually of that fuel they place in the water. But this is a nuclear fission reaction where we have a larger atom and it breaks up into smaller atoms.
The electrons, which are negative, are attracted by the protons, which are positive, and vice versa. But here in the nucleus are other particles with no electrical charge, called neutrons. Very important characters, too, as we shall see. And equally important when it comes to atomic energy is what scientists call the atom's binding force. It's a kind of cosmic glue holding the nucleus together. Then, in 1939, some scientists were experimenting with transmutation of uranium. What would happen, they wondered, if they fired a neutron at a uranium nucleus, already the heaviest in nature? Why not try? So they tried. And the result? Nuclear fission. Instead of a minor change, the atom split in two. Truly a discovery to change the world. For what had happened when the uranium atom split was a kind of double miracle of science. Half of the miracle concerned that binding force we spoke of before, that kind of cosmic glue which holds the atom's nucleus together. We still don't know all about that binding force yet, but we do know it is equivalent to mass. Therefore, we may speak of it as having a kind of weight of its own. Now, the two atoms into which a uranium atom splits also have binding force. But for some reason, it takes less of that glue to hold them together, and in the process of fission, a tiny fraction is left over. What happens to it? It explodes as energy, proving Einstein's theory that mass and energy are really the same. But we spoke of a double miracle. To understand the second one, let's slow down that fission 1 million or so times. A single particle starts the reaction, splitting the uranium atom. Here now is the release of energy as heat and blast. Here are powerful rays being given off, similar to X-rays. But here are free neutrons driven out with tremendous speed. And provided there is sufficient U-235 present, what science calls a critical mass, those neutrons bombard other uranium atoms, causing them to split and split still others. The result? A chain reaction. Over 1 million billion atoms exploding within 2 seconds. And the force? It would take Yankee Stadium full of dynamite to equal the energy released in the complete fission of an amount of U-235 the size of a baseball.
So in that video, it mentioned how in a fission reaction, the products have slightly less binding energy than the reactants, and so that mass energy, just according to E equals mc squared, that mass is converted into a lot of energy. One other way, another nuclear reaction that can happen is fusion. Now, fusion takes smaller nuclei, fuses them together into larger nuclei, like helium. This is when we talked about stars, this is how stars produce energy, is they take smaller atoms and they fuse them together into larger atoms. And in the process, they release energy. Now, fission and fusion have kind of some pros and cons. Fusion is hard to do. Fusion right now happens in the sun because there is such high temperatures and pressures that allows fusion to happen. So far on Earth, it has been difficult to get fusion to happen and to give us more energy out than what we put in. We spend so much energy producing high pressures and temperatures that we have a net loss of energy when we try to perform fusion on Earth. However, fusion produces cleaner products. We don't have radioactive products left over like we do in fission reactions that we kind of need to guard for security purposes. We don't need to do that in fusion reactions. The products are cleaner. And also we get more energy for less stuff. In a fission reaction, we produce around like 250 MeV, but that is for very large atoms of uranium, which are like 235 protons and neutrons. Whereas in fusion reactions, we get less energy, but we have way less stuff. We only have 2 hydrogen nucleons and another 3 hydrogen nucleons here, so that's 5. So we get a lot more energy for the amount of stuff that we have in a fusion reaction. Now, the reason why we don't have fusion reactors is we don't know what they look like yet. It's hard to do fusion in a way that we get out more energy than we put in. So that's kind of this week, looking at different types of decays and looking at comparing fission and fusion.